All right. Thanks everyone for being here. Mike Saunders. Today I want to talk to you about an intro to AV and EDR Evasion. Calling it Roll for Stealth. So, without any further ado, if you want the slides, you can get the slides at redsiege.com/stealth. And if you have questions about the talk afterwards, you can hit me up, Mike at redsiege.com. I'm Hardwater Hacker on Twitter. You can join our Discord. You can ask questions in there. All right. So a little bit about me. I am the principal consultant with Red Siege. I've been in IT a minute. And I like to do stuff that's not hacking, and I encourage all of you to get some hobbies that are outside and away from the computer. But let's talk about things we do on the computer. So before we talk about what this talk is, I want to get some expectations out there about what this talk isn't. This isn't an advanced evasion talk. We're not going to be talking about things like unhooking. We're not going to be talking about things like evading runtime checks for the most part. We're not going to be talking about ways to obfuscate your comms channels when you are doing something like a C2 beacon. But we are going to talk about, we're going to talk about an intro to getting past AV and EDR, things that you can do to get your payloads on disk or to get them in memory. Some things that you can do to evade the common, really brittle detections that are out there for basic AV and some EDR type detections. We're also going to talk a bit about entropy and what entropy is, what that means for us, and what we can do about that. So let's talk about things that get you caught. So one thing that's pretty common for getting code execution is things like the MS build technique, and that uses a template. Most people use a common template, and there are signatures there, but it could be other things. It could be a PowerShell script. It could be a batch script that you're running. Those types of things are going to have common default values if you're using from any publicly available source. Those publicly available sources are going to be signatured pretty quickly. Might work on day one when a new technique comes out, but pretty soon, if you think about something, maybe the MS build technique, that template's going to be signatured pretty quickly. And there are things in those templates that are going to be signatured, like variable names and function names. So you can see here on the slide, we've got a task that is a task name of class example and a task factory of code task factory. On the right side of that, we have some common things like we're declaring a variable to hold a memory address that we're allocating with virtual alloc. And then we got a variable called shellcode where our shellcode's going. So some very easily signatured things. There are a few other things here that might not be signatured depending on the AV and EDR, but things like hthread, thread ID, and pinfo by themselves probably doesn't mean anything. But when you can put them in something that's looking at in context, we just declared a variable called funcadder. We're then copying some shellcode into that memory address using a variable called shellcode. Now, hthread, thread ID, and pinfo might be signatured in that context. There are other things that might get you caught. Just thinking about things like PowerShell scripts. There are comments. It doesn't even have to be functional code. So this is an old blog article that I've got linked here, but the author is talking about getting caught running PowerView because of those 3 lines that are in the comment there. It's simply 3-line comment talking about what that function does, and that's what that particular AV signatured on. Black Hills has an article about bypassing AV to be able to run the Mimikatz PowerShell script. They also talk about some of those things like comments getting you caught. So be aware that even non-functional code that's in your templates and your scripts could get you caught. Also, not obfuscating common code execution patterns. So I'm going to talk specifically about the MS build template here again, but this applies to many types of scripts and templates and compiled code. Yeah, what you're seeing here on the screen is some C# code that we need to include if we want to use virtual alloc and create thread in our program. So we have to do something called a DLL import. And we DLL import from a particular DLL, in this case, kernel 32, and then we're importing virtual alloc and create thread. Now, you don't even have to use these for some AVs and EDRs to signal or to set off a detection. For instance, you could use a portion of the MS build template and just have these two declarations in there. You don't actually have to have the code that calls virtual alloc or create thread. You just have to have the definitions in there, that the DLL imports, and Defender will alert on that. Other things that could get you caught, this is dealing specifically with compiled code. And what you're looking at here is a screenshot of some output of Defender check. There's another tool that's a fork of this called threat check. They work very similarly. They take a file, they split it in half, they submit each half to Windows Defender to see, is there a hit in one of those halves. If there is a hit, it takes that half, splits it in half, submits both of those for scanning. And it keeps doing that binary search pattern until it gets down to exactly the bytes that are causing the detection. In this case, it happens to be some error messages that are in Mimikatz. This screenshot came from a blog that I wrote last year on bypassing signature-based AV. And you can see here, there's an error related to Mimikatz do local that is in the compiled code. And that's what's actually happening here, is those particular bytes cause the detection. So know that in your compiled code, you may actually have to go in and actually make a lot of changes to a binary if you're trying to stay hidden and you're using a well-known public project. Very frequently, I have to go in and I have to change the help messages. I have to change the error messages that the tool produces, have to rename functions, all kinds of things like that, just to be able to get the tool on disk and running. Not even talking about the the advanced evasion things like unhooking, bypassing ETW, and all that stuff. Another thing that could get you caught is entropy, and just know that it's a thing, and we're not going to talk about it yet, but we are going to get there. So we've talked about a few things that can get you caught. Let's talk about things we can do about that. So we need to make our tools, our scripts, our templates look like something that's not malicious. We need to blend in. So how do we go about doing that? This is a fun one, something that I would not have thought about until I encountered it. So what you're seeing on the screen is some output from a Windows Defender detection. It's looking at this file zoroptimize.exe and saying it's some type of Trojan. So what this is I had a shellcode loader that I had written that had worked for a very long period of time. And one day it wasn't working. It just didn't work anymore. So if you remember, back here when we're talking about Defender check, I'm running Defender check on my binary. I can see that there's these bytes. I can't really match it up to any strings, but I can see there's an error at a particular offset in the file, and it's the same bytes. So I make some changes, and the same thing happens. And for a little context, the shellcode loader used a XOR routine with a multi-byte key for encoding or encrypting the shellcode, rather. So I started removing bits of my program, trying to figure out where exactly it is that I'm getting caught, figuring it's with memory allocation or execution. Nope, it's not that. Figure maybe it's the way I'm copying shellcode into memory. Nope, it's not that. And I keep deleting bits of my code and recompiling, and I'm seeing that the same exact bytes are causing the detection in defender check or threat check. So now I'm really confused. I get down to the point that the only thing that's left is my XOR routine. And I try breaking it up. I try taking my XOR routine, adding in junk code, like declaring a new variable, adding a value to that variable, subtracting a value, adding two variables together, throwing in some sleeps, doing all kinds of things to just try to change what the code looks like. And the same exact bytes are being detected every time, which is odd. If I'm recompiling my code, I'm changing it, but I'm seeing the exact same bytes at the exact same offset every time. How is that happening? So I was talking about it in our internal chat, and Justin Polk, he suggested maybe it had to do with compiler optimization, to which my first response was, there's no way it could be compiler optimization. But then I realized that it really couldn't be anything else. And so I tried it. And sure enough, compiler optimization was what the problem was. I disabled compiler optimization. I ran threat check again, no threat found. So why is that? Why was no threat found there? Well, if you're not familiar with compiler optimization, it does multiple things. It tries to make your program more efficient in using memory, make your program run faster, make it a smaller executable on disk. And it does that by looking at what your program is doing, tries to look at it, says, oh, I see what you're doing here. We actually don't need any of this garbage. Or there's a faster way to do this, and reorganizes some things behind the scenes. This happens when it's being compiled. And as a result of compiler optimization, no matter what changes I was making to the code, it realized all the changes I was making were garbage, and it just needed to do this one particular thing. And that one particular thing, which is a XOR routine using a multi-byte key, is apparently something that doesn't happen very often out in the wild, because Defender had it flagged as malicious. So just disabling compiler optimization actually got me around detection. So now I compile pretty much everything without compiler optimization. That may bite me someday, but has not yet. So what's in a name? We talked about those entry points earlier. And what you may not know is that you can rename your entry points. So there are a couple of links here on the screen. You'll be able to get them when you download the slides. They are some Microsoft documentation that tells you how to go about renaming entry points. So what do I mean by that? Let's take a look at that. So this is a typical way of doing a DLL import for virtual alloc. This is bad. This is very likely to be signatured by every AV under the planet. And if it's not, it should be. But this is how it's declared in the 3G student MS build template, for instance. This is going to be bad. We're DLL importing from kernel 32 virtual alloc. But with a simple change, we can get around some detection. So this is a good way that still works today for getting around some AV and EDR. And it's not that different. If we look, there's what it was, and this is what it is now. We changed a few things. One, we specified the entry point. Entry point equals virtual alloc. So that means this is a specific entry point in kernel32.dll that I'm dealing with. I can add some options like set last error and exact spelling. And changing those options up can help evade detection, because remember, these detections, especially with AV, are very brittle. They're usually based on a signature, and changing any part of that signature breaks the detection. So I have seen cases where changing the order of set last error and exact spelling has been enough to get around detection. But the other big thing I want to point out here is the next line: private static extern int pointer splendid dragon. So before, it's like that, it's just virtual alloc. Here it's splendid dragon. Well, what does that mean? It doesn't mean anything. Yeah, that happened to be the combination of words that my random word generator came up with when I built this template using an automated tool. The key takeaway here is that this changed up the pattern. This changed up the signature. In Splendid Dragon, it's going to be different every time I run it. I run it, use a couple of words, and create a word pair and put that in there for my variable or for my function name. And then when I go to use virtual alloc later on in my code, instead of calling virtual alloc, I call Splendid Dragon. So this is one way that you can avoid detection for things like MS build templates or anything where you're compiling your C# at runtime on disk, whether you're using, or in memory, whether you're using a CSC or MS build or something like that. This is another way of avoiding detection. We also need to make our shellcode look legitimate. We need to make our shellcode look like it's not something bad. And the way we do that is by making it look natural, make it look like it belongs on the system. So how do we do that? One of the things we can do with our shellcode is structure our shellcode as a UUID, very similar to a GUID. It's a unique identifier, and it's structured in a specific way, and it's used to, instead of using a customer number, you apply or assign every customer a UUID. They have many, many types of uses. NCC Group did some analysis last year of a Lazarus Group shellcode execution method, and they found some interesting things. One was the way that the shellcode was being executed using an API called enum system locale. But what they also found was the way the shellcode was being stored. It was being stored as a UUID. And there is a tool that Bobby Cook put together called Ninja UUID Runner. And when you run that and feed it your binary shellcode, it will create a set of strings structured as a UUID that you can use. So this is what it would look like. You now have an array of UUIDs, or what appear to be UUIDs, but it's actually shellcode. So this is how your shellcode is going to be represented in your program until the point where you go to use it. The point where you go to use it, then you're going to run some type of function to transform that so that it's now a blob of shellcode that you can execute. But you can store it structured as a UUID. And this works to camouflage your shellcode. In many cases, this works to get around AV and EDR. We can also do some other things to hide our shellcode. We can just reverse our shellcode bytes and store them that way in reverse order. And then right when we need to use them, we flip it back around and dump it into memory and execute it. We could try breaking it up in chunks. And that does work. However, it's very cumbersome because there are going to be specific bytes that are signatured, whether you're using, an MSF Venom generated payload, whether you're using a Cobalt Strike payload, some other well-known C2 that has been signatured. Their loaders that are built into the shellcode are going to have specific bytes that are signatured, no matter what else about the payload has changed. And trying to break up your shellcode into chunks so that those specific bytes aren't next to each other can be done, but it's really cumbersome. And I would encourage you just not to go down that route of pain. There are different ways you can approach it. One thing you can do is take your shellcode and divide it into two arrays. This is something that Justin Paulk came up with one day. And take your shellcode and store it in two arrays, an array of even and odd bytes. And I don't mean even and odd as in the shellcode value. I mean the position of the byte within the original shellcode array. So if you think of a shellcode array, starts at byte 0. That is going to be your first even byte. And then the second byte of shellcode, which is byte 1, that's odd, and so on and so forth. You break up your shellcode into 2 arrays of even and odd bytes. Now there's no chance that those bytes are going to be contiguous and result in a signature, or it's very unlikely that that's going to happen. And then when you need to use your shellcode, you just read through each of the new arrays that you've created 1 byte at a time, flipping back and forth until you've reconstructed your shellcode. Another thing you can do is steganography, and this is something that is used frequently by various types of malware, crimeware groups. Steganography is the act of encoding encoding data in an image that you're trying to hide. So imagine taking a message and you encode it in a picture, and then you send that picture. You can just have that picture out on a web page, and someone can come and download that picture. And if they know the key and they have the right program, they can feed the key and that picture into the program, and out comes the secret message. So you could store your shellcode in the image. It works by encoding data into the least significant bytes of the color data in image. And you can store a lot of data in an image without increasing the size of the image and without degrading the quality of the image. So steganography is definitely something that could work for you, and you could take a look at. Another concept is this concept of a big integer. SubT tweeted this out a while ago, and I will say that I have not had time to play with this to see if it works. However, if SubT tweeted it out, I'm quite sure it actually will work. Big integer takes a byte array as a constructor argument. And what is our shellcode other than a byte array? So big integer could take shellcode as a constructor argument. It would look something similar to this, but there's some steps to convert that back from a big integer into a manner we could use. But that might be something that you could use to bypass detections. So I've talked about entropy a couple of times. I told you that we would get into it, and so we're at the time where we're going to talk about entropy. I want to preface this conversation by saying that I am not a mathematician, so I may not be explaining all of this stuff 100% correctly. I will tell you that we're talking about entropy in the context of information theory, not the heat death of the universe. There are some different kind of definitions for entropy. We're talking about it as it pertains to information theory. We're also going to be talking about something called Kolmogorov complexity and compression and how that relates to entropy. So, roughly, something that is high in entropy can be said to be more random. So if something has a high amount of randomness, it's very random, it is high in entropy. Conversely, something that is low in entropy is less random. Now, I mentioned Kolmogorov complexity. Kolmogorov complexity tells us that higher entropy data is less compressible than lower entropy data. In other words, highly random data is less compressible than non-random data. We can test this. I've got a simple example here on the screen using DD. We're going to read in 1 million bytes from dev urandom. We're going to pipe them into gzip and see how much it compresses it. We do this, we can see that it compressed it. It reduced the size of the input by 0.0%. Highly random data, which reading from dev urandom should be highly random data, is not compressible. It is not compressible because it's high in entropy, and we know that because Kolmogorov complexity tells us we can't compress it. So why are we even talking about this? Very frequently, we use encryption to obfuscate our shellcode. We'll use whether it's ARC4 or AES 256 or a Zora routine or something, we use encryption that protects our shellcode. But using encryption actually drives up the entropy in our resulting file that we're including that shellcode in. It is more random. And as a result of having more random data, because we used encryption, the entropy in that binary is higher. And if something is looking at entropy as a means of deciding something is trustworthy, then that could end up being a tell. Hey, there's a lot of randomness in here. Now, before I continue, a little bit of a sidebar. Earlier, I talked about, that you should change your default variable and function names. That is good. So doing that in your PowerShell scripts and your MS Build templates, things like that, that is very good. However, you should not just change it to a random string of characters. And the reason you shouldn't do that is because of entropy. I have ran into AV and EDR that looked at the variable names that were in scripts, and simply using randomized strings for the variable names resulted in a detection. But replacing them with words, it bypassed detection. Now, you may be tempted to just grab a single word and use that word as your variable and just do word replacement. However, I would caution against that, because you may run into instances where the word that you've selected from your dictionary is a reserved word in the language that you're developing in. This is an even bigger problem. It's an even bigger problem in VBA, I'm told. I've ran into, there's a lot of reserved words there. I get around this by generating word pairs. That's where Splendid Dragon came from. Obfuscated Diamond, Roly Poly, whatever it is. Have a dictionary of words, grab 2 words at a time, pair them together, and now use those 2 words as your replacement for virtual alloc, for instance. And very unlikely by combining those 2 words that you're going to end up having a collision with a reserved word in your programming language. Now, more on entropy. We said that random data is high in entropy. Encryption drives up entropy. So how do we counter that? Well, let's consider something. We know that languages are not random. And I'm talking about languages like English, German, French, Spanish. They are not random. And we can test this. The first example, I've got an English dictionary. I'm going to compress it with gzip. I reduced the size by 64.7%. Compressed it quite a bit. So that tells us that the English language is not very random, because we reduced the size of the input by almost 65%. Tried it with German, compressed it by 75.9%. So that means that German is even more compressible, meaning it's even less random than the English language. Now, there are 2 very interesting PDFs that I've linked here that are talking about using basically like written word as a way of obfuscating your shellcode. Basically, you could, instead of having shellcode, you could have Shakespeare, and that would be your shellcode. It's very interesting. We'll talk about that in a second. Yeah, it's very interesting technique, and I've actually seen it work. It works really well, and it's mind-blowing, and you should read those papers. So Deadless asked about will Stego will help with ingress and egress. You do have to extract it for execution. Yeah, absolutely. You're going to have to extract the shellcode out of that image, and then you're going to have to put it someplace in memory and execute it. So there are definitely there's more evasion that's needed. And again, this is the 101 level talk. This is about getting your payload on disk. the actual next steps of evasion, where you're unhooking or patching ETW and things like that, that's another talk. But yes, Stego will help with getting data in or getting data out of the network. So why are we even talking about entropy? Well, like most things that I talk about, it's based on experience. So story time. I'm on a test, and this test has CrowdStrike on the endpoint. And this particular CrowdStrike instance had CrowdStrike's machine learning AV component enabled. So in addition to having the behavioral things that happen when you have EDR, it also had an AV component. I had a shellcode loader that used AES 256, encryption to encrypt my payload and hide the shellcode, I should say. And I dropped the shellcode loader on the target machine, and I tried to execute it, and nothing happened. And I don't mean like a window opened up and then it terminated. I don't mean that my beacon checked in and then it stopped responding. Just it's as if nothing happened when I double clicked on it. So that seemed odd. And I recompiled my loader, and like any good developer, what I did was I threw in a bunch of printf statements. Basically, got here, got here, got here, so I could see where in the code it was breaking, and I uploaded that, and I executed again, and I got nothing. The very first thing that program should have done when it loaded was printed off a statement that said, like, I've started running. It did not start running. I didn't get that output. So that told me that something on the system has determined that my payload, my shellcode loader, is untrustworthy for execution. It's not even allowing it to start running and then terminate it because of badness. It's just decided it's not good. So I started thinking about why that could be, and I talked to some people about it, and came up with the conclusion that it was probably related to entropy, because I've got a Cobalt Strike beacon in what's otherwise a very stripped down shellcode loader. It's got very little code in it. In fact, if you strip out the beacon, the compiled size is tiny. There's almost no code in here. But you know, you throw in a beacon in there and you've got 10 megs of shellcode, and now you have a very large executable that is very random because I'm using encryption. So the entropy is high. So I thought about ways of getting around AV, and there are some different ways that can happen. What I happened to do was I just compiled in my shellcode loader an array of words, and the reason that I threw these English words in, because we just talked about languages aren't random. So if I can add a bunch of non-random data into my shellcode loader that has high entropy because I've got encrypted data, if I can also now throw in a bunch of non-random data, I can drive down the overall amount of entropy that is in the loader, the average entropy. So this actually worked. Mind blown. This was enough to get around CrowdStrike. Now, keep in mind, I still had to have my method of loading that shellcode, executing that shellcode. All of that had to evade detection. But this was enough to get the payload on disk and get the payload running. And it looked, well, actually, that was me. Thanks to Jargon for that. But that's what my face was like when that happened. This is what the code looked like. I created a variable called anti-entropy, and it contains 7,740 words. There is no magic to that number. That is how many words were in the dictionary that I was using. I compiled these in, and I disabled compiler optimization because many compilers will see that this variable was not used anywhere and discard it. So with compiler optimization disabled, I recompiled my shellcode loader. I now have a shellcode loader that has my encrypted shellcode and all of these words. And this was Oh, awesome. We got some great spam in the chat. This was enough to drive down the entropy in the shellcode loader to a point where it no longer was suspicious, according to CrowdStrike. Now, if we take a look at it, we can see why. I've got two files here. I have aes.exe, which is my shellcode loader with my Cobalt Strike shellcode encrypted as using AES 256 encryption. When I try to compress it, I can only reduce the size by 18.4%. But when I take the AES plus words, I can reduce the size by 97.8%. That means the majority of that loader was not random data. It was highly compressible data. Now, it was 15 megs in size, which was not ideal, but I was able to drive down the entropy to a point that CrowdStrike, in this case, decided it was trustworthy. And this is by no means a slam on CrowdStrike. There are lots of AVs and EDRs that use entropy as a measurement for determining whether or not something is trustworthy. And you know, in this case, it happened to be CrowdStrike, and it worked. Another interesting technique that's related but not the same came out in 2019. These researchers came out with an article called Silence, I Kill You. They took Silence's next-gen machine learning AV component, buzzword bingo, mark your spot. They took that AV component and they did some analysis. And they were looking at how could we get a payload around this. And what they ended up doing was extracting the strings from a popular game at the time, a very popular game. And they found that by appending those strings onto any binary, Silence would let the binary run. Now, in this case, it wasn't an entropy thing. It happened to be specifically because of these strings, enough of these strings were present that Silence went like, oh, you're that game. I need to let you run. And so that worked. But these techniques could work against a lot of different AVs and EDRs. There's a lot of research that can be done and new techniques that could be had. I happened to compile in some words into my binary, and that worked. But that wasn't the only thing that I could do. You could literally take a picture of a cat and cat a picture of a cat onto the end of your payload. Your payload will run, and the amount of entropy is going to be low, and or it's going to be lower. It's going to be significantly lower. And now you've catted a cat onto your payload. So Justin Elsie threw out a comment here. If you have Mac brew, all right, if you have a Mac, do a brew install ent and use the ent tool, or you can use that on Linux as well, and that will calculate and compare entropy between files, and that works well. So that is a great tool. Thank you, Justin. Actually, I have used ent before, but at the time I couldn't remember what the tool was, but I knew that the gzip trick works. So ent is another tool you can use. So a little more on evasion. I got to thinking about this topic of entropy and using words, and how could I use that to my advantage? Well, what if I had a tool that would replace every byte of shellcode in my shellcode loader with words, so that my shellcode loader literally contained no shellcode? So I came up with a tool called Jargon. Jargon is special words or expressions that are used by a particular profession or group, and they are difficult for others to understand. So that is Jargon. You can get that on my GitHub. That is available. So how or what is Jargon? Jargon takes shellcode. It encodes those words. Each byte of shellcode is English words. And as a result, we avoid having any raw shellcode in our payload. And because we're using words, and we know that languages are not random, they're lower in entropy, we're going to have a lower entropy payload than we would have if we used encrypted shellcode. So how does it work? Most of you are probably aware that you can store shellcode as hex bytes. So if you want to store a 0, you store 0x00. What I did not know until I started this journey was that you can store it as an int. So for every hex byte that you have, you could convert it to an int and store the int instead. So store a 0 instead of 0x00, store a 1 instead of 0x01. So if we know that we can store shellcode as an int, we can use that to our advantage. We create a translation table. And the translation table needs to have 256 words, and they have to be unique because there are 256 possible shellcode values, 00 through FF. Each position in our translation table corresponds to a byte of shellcode. So in this case, attending is in the first position in the array, position 0 or 0x00. This is shellcode byte 0. So anytime I want to store shellcode byte 0, I store the word attending. Anytime I want to store the shellcode byte 1 or 0x01, I store it promptly, and so on and so forth. Now, I've used an English dictionary, but the source words could be anything. The source words could be the strings from kernel 32. The source words could be strings from a Chinese dictionary if you're trying to emulate some type of APT and really set off some alarms. A lot of different things you could do. You just need to have 256 unique values, and the dictionary you're selecting from, the words need to be valid string literals in C. So we talked about how this works. Attending is position 0, it's 0. Promptly position 1 represents a 1. So now we use some type of script to encode our shellcode. So this happens to be a Cobalt Strike beacon that I've got here. The first byte in my shellcode array is Dutch, whatever byte that maps to. Dutch, sheriff, prepared, emotional, prepared. You can see there, I went on to the second prepared to show that things repeat because shellcode has bytes that repeat, right? So whatever these are, they map to some values. So our payload that we're going to execute is actually going to contain this table, the translated shellcode table. It's only going to contain words. There are no shellcode bytes in here. Now, to actually get our shellcode at runtime, we need a simple loop. We're going to set up 2 loops. In the outer loop, we're going to loop through each byte in our translated shellcode. In this case, position 0 through 265,730 because the shellcode's 265,730 bytes long. And then for each byte of shellcode, we're going to do a second loop. We're going to look at our translation table. And we say, does this byte match this position in our translation table? If it does not, increase the position in the translation table. Do they match? And continue on until you get a match. And if you get a match, that position in the translation table is your shellcode value. Because if you remember, we looked at this. If it matched in the first position, position 0, that means attending, the word we're looking up, is shellcode byte 0. If the word was promptly and we get a match, that means we're at shellcode byte 1. So we run through this loop, we decode our shellcode. We now have shellcode bytes that we can execute. And it has some trade-offs. It's much larger than my shellcode loader that is, you can see here, it's 1.7 megs, but I'm able to decompress it, or I'm able to compress it by 85.8%. So that means it's got relatively low entropy because it does not contain raw shellcode bytes. But does it work? Well, let's try it. We run our shellcode, and boom, our beacon checks in. So this was a shellcode loader that was constructed using only words. There were no raw shellcode bytes in there. And at runtime, we decoded that and we loaded that shellcode and executed it. So this technique does work. It's out on my GitHub. You can grab a hold of it and use it in your own tools and play around with it. It's available, github.com/hardwaterhacker/jargon. A couple other things. I will say that I'm not the only person that has come up with this idea. I'm just the first person who's written it publicly that I could tell. I couldn't find any other public examples of this at the time that I did it. Sometime later, I heard about a talk that was at DEF CON this year using emoji as shellcode. So translating your shellcode bytes into emoji. I believe this is for RISC-V architecture or RISC-V architecture. And so it doesn't work with Intel right out of the gate. However, you probably could translate this and use shellcode use emoji as shellcode. So there are other ways to skin this cat. If you're using Cobalt Strike still, know that there are some changes that you should make that can help you here. Simply recompiling the artifact kit, or what's now the arsenal kit, can be enough to get you around some janky AV. But know that that is very heavily, you can extend it quite a bit and modify how it works. Moving to other C2s is probably the direction most people are going, but know that you can still wring some more life out of Cobalt Strike by working with things like the artifact kit and the user-defined reflective loader and things like that. But those techniques are for AV Evasion 102 or higher. That's the next talk. I will recommend taking a look at the Sector 7 courses, the Red Team Operator Malware Development Essentials and Malware Dev Intermediate courses are great resources that have some really cool techniques that I didn't talk about here, but you should definitely check it out. They've really helped me up my evasion game. So if you want to get the slides, get them at redsiege.com/stealth. You can get the slides today. You can get the tool on my GitHub. If you have questions or want to get in touch, I'm Mike at Red Siege. You can hit me up on Twitter and now on the InfoSec Exchange Mastodon. I am Hardwater Hacker. Follow Red Siege on Twitter and join our Discord. Get in on our Discord. Feel free to come in and ask questions, share about new things that are going on with you. We'd love to have you and love to hear what you have going on. So that's what I got. I'm paying attention to the chats here to see if there are any questions.
I don't think there are. If anybody has any more questions, get them in now. I know we had a Tim coming here, but I think his stuff couldn't connect. So if nobody has any questions, I appreciate you joining us for this SIEGECAST, and we will see you next time.